Everybody has 6.2 notes. Okay. Guys, today what we want to start looking at is titled Exponential Growth and Exponential Decay, and it's going to be very similar to what we did in the last section that involved exponential functions. And the thing that we're going to look at is what a percentage of change does, either positively or negatively. And we want to see how that affects how growth and decay are established within this. So, the first thing we're going to ask ourselves today is the following. What are some of the characteristics of exponential growth and exponential decay functions? And in order to be able to answer that question, we need to be able to use and identify exponential growth and decay functions. And then we're going to apply them to solve real-life problems involving exponential growth and decay. So before we can even go on, we need to know a few vocab terms here. And then once we have established what those are, I think that the stuff that we look at today is going to be very simple, because really what we're doing today is pretty much the same stuff that we did in the last section. They're just going to go about it in a different way. Kaylee.
Okay, so you know how yesterday on problem 26, how we couldn't figure out the equation? They put it in...
As a fraction 3/2, which miffs me, because it's the same thing. Yep. But that's, you know, part of the reason for mistakes like that is why I always round up the next half a point anyway. So, makes sense. Because I know that there's some glitches yet, and they do too. So, but good thing to know is that you were right? And you'll still get your points. So no harm, no foul, all right? No harm, no foul. All right, here we go, guys. First vocab term up here, exponential growth. How about a volunteer to read that definition for me, please? Exponential growth. Who wants it? Go, Kaylee.
When a quantity increases by the same factor over equal intervals of time.
Okay, so it increases by the same factor. So let me talk about this example. If I cut something in half or if I double it, which one is increasing it? Cutting in half or doubling? Doubling. So we looked at functions in the last section where we might have had an example like this where we said, hey, what if y was equal to, say, maybe we started with a 3 and then we doubled that. So what would my change of factor be, guys? 2 to the x power. Okay? This is going to be an example of exponential growth because that b value is greater than what value? Well, 1. Okay? That b value is greater than 1. So that represented something that was going to be exponential growth. Now today, we're going to look at something called an exponential growth function, and we relate this differently. The exponential growth function is really the same as the exponential functions that we looked at. We're just going to go about it differently in terms of how we come up with our function. So, right here on the second one right here, guys, exponential growth function. It says it's a function of the form y equals a. A is like our starting value. Instead of having b right here in the middle, what do you have now? 1 plus r. 1 plus r, it says where a is greater than 0 and r is greater than 0. Here's what I'm going to tell you. R is a percentage. R is some percentage. In this example, I'm going to use 25% maybe. Okay? I want to use 25%. So anytime you hear about this letter r, or if you ever see a percent, you know that that's going to take the place of the variable r. Now, when you substitute stuff in, you need to make sure that percentage is a decimal. So if I want to write a function of exponential growth form for 25%, the first thing I need to know is, hey, what the heck is 25% as a decimal? 0.25. So you've got to turn percents into what? Decimals. Okay? So here's how this would look. Suppose we had a function y that was equal to, let's start with 3 again. And we're going to increase that 3 by 25% each time. So by this formula for exponential growth right here, we have to do 1 plus r, where r is a decimal. So what's 25% again as a decimal? So what would the 1 plus the 0.25 be? So 1.25 and to the t power. Okay, 1.25 to the t power. Think about it, guys. This is like my b value now. This is saying you're increasing stuff by 25%. So your growth factor is 1.25. Does it make sense here? I told you exponential growth, this b value had to be greater than what? 1. When I take 1 plus 0.25, is that greater than 1? So this has to represent exponential growth. You bet. Exponential growth there. Okay? Well, we talk about growth, decay is just the opposite. Instead of increasing, it does what? Yeah, it's when a quantity decreases by the same factor over equal intervals of time. So as an example, how about we start with 3? And instead of doubling it this time, let's cut it in, maybe say, half. Cut it in half. Well, what fraction or what decimal could I use to represent half? 0.5. This 0.5 right here to the t. So what this is really saying, hey, your b value is between 0 and 1 right there. That b value is going to be between 0 and 1. B value between 0 and 1. So for an exponential decay function, instead of adding a percentage, what if I say something decreases at a certain percentage? Do you think we're going to add that percent, or you're going to subtract that? You bet. Exponential decay function. Again, let's pretend our rate is 25%. Rate's 25%. So an exponential decay function is any function of the form y equals a times this time 1 minus r, where r is that percentage rate as a decimal to the t. A's got to be greater than 0, and r is between what and what, guys? 0 and 1. Is 25% between 0 and 1? No. What's 25% as a decimal? Is that between 0 and 1? You bet. So let's look at this example right here. Exponential decay would become the following. Y equals, let's start with a value 3 again. All right, here we go. What would 1 minus 0.25 be this time? 1 minus that percent. 0.75, right? Think about this. How many of you guys have gone into a store, saw a sign while you were shopping, 25% off? You've seen stuff like that before, right? If something's 25% off, what percent are you actually paying for then? 75% of it, right? That's why that 0.75 is in. You're paying for 75% of it, okay? All right. Then the last formula I need to show you is compound interest, okay? Compound interest. I'm going to put a formula up here, and then we'll talk about what it means. But guys, if you ever see something about compound interest, here's the formula we're going to know. All this is about investing money over time in a bank. Now they're going to talk to you about terms like you invest it annually. What's annually mean for banks? What time frame? That is 1 year. What does quarterly mean? How many times does it get compounded in a year if it's compounded quarterly? 4 times. Let's see, semi-annually. How many times is that compounded in a year? 2. How about monthly? If something was compounded monthly, how many times does that get compounded in a year? 12 times. How about daily? 365. So you know those values. So the formula I want you to know right here is the following. Write down your balance that's left is equal to a capital P. All right? Compound interest is the interest earned on your principal and previously earned interest. I'm going to say the following. A new balance in my bank account would equal my principal P times, here's the formula, 1 plus R over, this is a goofy formula, R over N to the NT power. Oops, there should be a T right there on the end. Now I'll tell you what all these mean right here, okay? This P value is like the value you start with. R again is going to be your percentage rate. And then N is going to be the number of times you compound annually. Call it number of compounds. Just have this formula down. We'll look at an example here in a second. But just have those down. That's the formula you're going to need to refer to. And this formula is used anytime you start talking about money being invested at a certain percentage rate. Let me know when you've got everything down before I proceed here, okay, guys? Right, We good, guys? Yeah? All right, great. Great, great, great. Anybody need more time? All right, let's rock and roll. Let's get into the gist of this today. How about a volunteer to read example 1, using exponential growth functions? You want to read number 1 for me? Oh, come on. Thank you. Inaugural.
Inaugural attendance of an annual art festival is 80,000. The attendance Y equal increase by 6% each year.
Okay, the word inaugural means the following. In 2010, the Twins opened up Target Field for their first season. They called that their inaugural season, so like the first season in Twins baseball at Target Field. So inaugural means the very first time it ever happened. So as an example right here, guys, what was the starting attendance to begin with? What was the first attendance ever at this art festival? 80,000 is like the starting value. And this is increasing by what percent, guys? 6% each year. So to write an exponential growth function that represents the attendance after t years, here we go. We're going to say y equals. All right, what was the starting value again that we're going to come up with? 80,000. Now we've got to put this growth factor in here in terms of a 1 plus the rate or a 1 minus the rate. Since this is an exponential growth function, are you adding 6% or subtracting 6%? Adding. This is the 1 plus r part. So let's see. 6% is a decimal. What would that look like? 0.06. So 1 plus 0.06. What's that get you? 1 plus 0.06. What's that get you? 1.06 to the t power. There it is. 80,000 times 1.06 to the t. Guys, is that b value above 1? Is that growth factor above 1? It's got to be exponential growth. Now, next question says, how many people will attend the 5th year? I'm not even going to round to the nearest 1,000. I'm just going to get it round to the nearest whole number. All right? How am I going to solve this, kids? How am I going to solve this? Attendance during the 5th year.
1.06
Times 5?
T.
So take it times t. What is t going to be? 5. Now, am I going to take it times t or take it to the t power? Am I going to take it times t or am I going to take it to the t power here? There you go. So here's the deal. Inaugural attendance, 80,000. All right? Good morning, Mrs. Jensen.
Good morning.
And then take that times 1.06 to which power again, Alana? 50, say? Ah, boy, this is not working very well today. Slap a Ford sticker on it. All right. So let's evaluate. Let's do that. So I'm going to go 1.06 to what power first, kiddos? And then what do I have to multiply by now?
80.
Times that by 80,000. So all right, so that's about 107,058 people. So after the 5th year, what's attendance? What did I get up there?
107,058.
Okay, very good. 107,058 people. All right, that makes sense. Is that more than the 80,000 or less than the 80,000 we started with? It's more, isn't it? Okay. All right, great. So I think we're okay with this. Let's look at example 2. How do you identify if something's exponential growth or exponential decay or neither? All right. This is just like going back to yesterday and saying, hey, if something is going to be exponential, that common difference, or I'm sorry, that common factor has to be the same. Okay, that common factor has to be the same. So I'm going to look at example A right here. I want to know, is this growth or decay? First of all, look at your y values, guys. From 24 to 12 to 6 to 3. Are my values moving up or are they moving down? So if it's anything at all, it would have to be decay, wouldn't it? Okay, so the way we check this is to look at our change factor. So here's what I want someone to do. Guys, if I took 12 over 24, isn't 12 half of 24? Isn't 12 half of 24? It is, isn't it? Check the next one. Is 6 half of 12? If I would divide these out, 6 divided by 12, what would you get as a decimal? 0.5. Is 3 half of 6? So in each case right here, the change factor that we come up with is 0.5. Comes from 12 divided by 24, 6 divided by 12, 3 divided by 6. That change factor is the same. Now that 0.5, is that a value above 1 or below 1? Below 1, indicating growth or decay. Decay, you bet. Now guys, if those growth factors or decay factors that we come up with are not the same, in other words, if we didn't get 0.5 every single time, could I say it's decay then, or would I have to say neither? You want that common factor to be the same every single time. Check the next one, kiddos. What's 40 divided by 4? 10, isn't it? 400 divided by 40, what is it? 10. 4,000 divided by 400? 10. Let's see, how's that 10 related to 1? Does that indicate growth or decay then? It's got to be growth, exponential growth. Guys, didn't we do this in the last section right here? We did, didn't we? We did. They're just talking about this in different terms now. Same thing, they're just talking about it in different terms. Okay? All right, page 3 for me quickly. All right, guys, interpreting exponential functions. First thing we're asked to do is determine whether each function represents exponential growth, exponential decay. Once we've identified that, we need to identify the percent rate of change. Guys, look at this first example right here. What value do you start compounding right off the bat? 4. This A value is 4. This growth rate is 1.09. Let's see. Is that going to be exponential growth or exponential decay? I already answered it for you. Has to be growth. B is bigger than 1. Growth. So by formula right here, guys, by formula, if it's growth, 1 plus our percentage rate had to equal that 1.09. So guys, what decimal did I add to the 1 to get to 1.09? 0.09, right? So guys, when it says, what's this as a percent rate of change, how would you turn that decimal 0.09 into a percent? Or what percent is 0.09? It's 9%. So it's a 9% rate of change. Second one, same thing. Look at your B value here. Above 1 or below 1? Below 1. Growth or decay? It's decay. Not tooth decay, exponential decay. Although if I keep eating those things over on the desk that are so sour and good, I'm going to have some tooth decay. Did you hear me, Holly Wands? Let's see. So if I'm talking decay, we're talking about the formula 1 minus r, and that 1 minus r equaled 0.93. Guys, what did we have to subtract from 1 to get down to 0.93? 0.07. So what's that rate as a percent? Shout it out. What's that going to be as a percent? 7% change, you bet. 7% change. Okay. That's pretty easy, isn't it? Yachty or naughty? Pretty easy? It's pretty easy. All right. Hey, this is the one example 4 you might want to put a star by. I had said if you ever get an example that starts talking about investing money right here, run to that one formula that talks about compounding interest. Okay. I'll read example 4 and then we'll see if we can't figure some stuff out. Guys, number 4 says the following. You deposit $300 in a savings account. So how much are we starting with? $300. And we're investing at what percent? 3%. But we're not just compounding that once a year. It says it's compounded how? Monthly. So how many times are we going to get some extra interest on our investment? 12 times in a year, right? It says write a function that represents the balance after t years. So here's the deal. This example is going to be important because we're going to compare it to the next example and see what's going to be the better option for us. Here we're getting 3% compounded how? Monthly. All right, and we'll see how that compares to what we look at here in example 5 in a second. But this is that goofy formula. I'm going to write that formula down again quickly. It says the balance of your investment, or the balance of your account, is equal to the amount you start with, P, which stands for principal. And I don't know why this is not working. Times 1 plus R over N to the NT power. Okay, let's figure some stuff out over here first. Guys, what's the principal? What was the initial investment? What was my P value? How much did we start with?
300.
Oh, my Lord. $300, right? What's your R value? What's your percentage rate? %, right? R is 3%. Sure, now you work. I get the other marker out. Now you want to work. Okay. How about the N? How many times are we compounding this? 12 times, right? Let's fill in what we know. My balance B, it's going to equal the following. What are we starting with again? $300 times 1 plus, all right, what's the R value? So 0.03 divided by the N value. How many times we compound it? So 3% is getting divided out over 12 periods. And then this is getting compounded 12 times in a year. All right, so 12t. All right, so I want to change some stuff right here. I don't like that number that's in the middle there in parentheses. I don't like the 1 plus 0.03 over 12. So somebody do this for me. Let's go 0.03. Let's take that 0.03 and divide that by 12. What's my decimal that I get? 0.0025. Now we're going to add that to what value right here? 1. So the way I'm going to write this here, guys, is the following. My new balance that I have, B, that's going to equal the $300 we started with times 1 point, it was 0025, right? To the 12t, like so. Can you handle that first of all? You okay with that? Okay, that would be the function for earning 3% interest over 12 months of compounding that interest. Okay, that would be the function you would need right there. All right, so what percent interest am I earning? What percent are we earning? 3% compounded how? Monthly. Now we're going to come back to this and we're going to graph this here eventually compared to example 5, and we're going to see what the better investment is. The more I compound money, the quicker the balance grows. Okay? And I want to compare this then in example 5 to what we have in example 5, I should say, where all of a sudden, guys, here's a table that says, hey, here's a real life problem, and a table that's going to show you the balance of a money market account over time. So guys, at the very beginning, what was our balance? What was our balance here? What's the beginning balance? 300. We're starting with 300. This is what we start with right here. We start with $300. So we need to write a function that represents the balance after 2 years. Now notice right here, every time they compound this, it just goes from year 1 to year 2 to year 3 to year 4. So this is only getting compounded annually, once a year. So the end value is really what value here? 1. Okay? So my function is the following. Y equals the starting balance of 300. Guys, how am I going to find that B value, or rate of change? How do you find that rate of change? What do I have to do? How do you find your change factor in any table? Anybody? Look at what I drew up there. Yeah, take 312 and divide it by 300. What is that value? What is it? Somebody punch up 312 divided by 300 for me. 1.04. So this problem right here, let's see, what percent interest are we earning here? 1.04. What percent are we earning? 4%. Let's see, in the last example, we were getting 3% compounded monthly. Here we're getting 4% annually. Okay, so this would be the function right here, 300 times 1.04 to the t power. Well, all right then. What we want to do is we want to graph the function from example 4 and this one from example 5 and see which one's the better investment. I want to know if 3% over 12 months is better than 4% annually. So we're going to plug both of these in. Anytime they ask you to graph something, where am I going to tell you to go? We'll go decimals here with us. So check this out. I'm going to change some stuff around. You guys help me remember the functions. All right, so let's get into decimals here. There it is. All right, jump back to example 4 for me. Who's at example 4? Anybody? In example 4, what kind of a function did we come up with? Okay, what was that one from example 4? Y equaled, was it 300 to start, guys? And then in parentheses, did we have 1.0025? And that was just to the 12t, was that right? So I'm going to raise that to the 12x. Now nothing shows up here, so I've got to get a window in here that works. So my window I need to change. Guys, what was the amount? What was the highest amount of money in that table in example 5? What was the highest amount? 365. Okay, 365. So I'm going to change this y value here on the end to about 400. How much money did we start out with, guys? How much? 300. that table, let's see, that table went from year 0 to year 5. So I'm going to change the x up here from 0 to 5. All right, here's a graph right here that represents the first one. This here is my 3% graph compounded monthly. And exactly what we expected to happen. Starts at 300, value starts rising. So I want to know if that's better than 4% annually. So I'm going to plug in my other graph, y equals, what did we get on that last graph? Y equals 300 to start with. What was our percent, or what was our B value? 1.04. And then that was to the t power, right? I'll call it x right here. Guys, which graph wins out, the blue one or the red one? The blue one. And that blue one is this graph right here, which was compounding 4% annually. So my question becomes the following. Once I've got those two in there, which one's going to be my better investment? 3% compounded monthly or 4% annually? 4% annually is going to get you a better return. Graph is higher. There's more money in there. Okay. So when we say we're comparing these right here, here's what we come up with for a comparison. Graph these functions in the account. Okay. You want to say the 4% annually is a better choice. And I'm going to write it this way. 4% annually is a better financial decision or a better financial investment. Okay, so the big idea here today is this. When we talk about exponential growth and decay, A value is the same. That growth factor that you come up with anymore, it's either 1 plus R for growth, 1 minus R for decay. And if they ever talk about compounding something more than once in a year, you have that compound interest formula to look at. So, questions about any of the examples we went over here first of all today? Anybody? I have a question for you guys. Compared to last section, really much change here? Not really. It's just a little different setting stuff up. But once you get once you've got that stuff set up, doesn't it just become the same process as the last section? Okay. All right. Here's what we're going to do then. I'm going to go ahead and stop this.